Last time we were starting out in this chapter, moving beyond linearity. And as you could see, we looked at some concepts such as polynomial regression, step functions, regression splines and smoothing splines, maybe even a bit of local regression. And the overall idea is that these are all motivational for how generalized additive models work. What we'll do today is look at the conceptual and applied exercises from this chapter. And before I forget, I do want to highly credit the resources that were available online, such as this GitHub repository by a person named Onmi. Most of the work and notions come from them. What I did today was clean up some of the mathematics and maybe a couple of the plots. As usual, for the folks in the audience, feel free to let me know when you want to stop and talk about a particular spot. Otherwise, I'm going to read through many of I think we have up to 11 exercises, but we do not have to cover them all.
Right.
Problem number one, the idea was we could do cubic regression with splines. Our usual basis functions are the power functions x squared, and x cubed. But perhaps you want this strange recentered function that's one-sided, that it only takes values coming in from the right, where we have a knot or an intersection point at x equals c. We could have a new function of this form with the usual basis functions, but also another term at this strange addition as well. What problem number one asks us to do is to make sure that even though we have this piecewise function, we could still assure that this is a cubic regression spline. So first of all, if we have a generic cubic polynomial with these coefficients a1, b1, c1, and d1 for all possible values of x less than or equal to c, we are asked to find what these coefficients a1 through d1 are in terms of the beta coefficients. Now, if we are in the piece that is x less than c, the strange new piece is simply 0 at this point. So this term is not existent yet. Thanks to some code that I saw in another R4DS book club, I placed all the answers today in these drop-down menus that are simply convenient HTML code that I did not know about before. So for this particular exercise, we have a trivial answer that the A1, B1, C1, and D1 coefficients are the original betas. Now, in part B is the harder notion. Looking at the piece where x is greater than c, now we need to worry about this new term with beta 4. I did not bother to type out all the mathematics, but the idea is you plug in all this and you worry about what would happen near x equals c, and you do that the same thing with this broader polynomial as well. The math would have taken up a lot of room, but when you combine like terms, that is the constant, the degree 1 term, the degree 2 term, and the degree 3 term, we find that the A1, A2, C2, and D2 coefficients can be written in terms of the original betas as such. At this point, we have shown that the new f of x function, that is this one up here, that the new f of x function is a piecewise polynomial. But if later on people wanted to use this polynomial for predictions or something thereof, we would hope that it's still continuous, maybe even differentiable or smooth. To show that it's continuous at Cassie, for the left piece and the right piece, we plug in Cassie and verify that we do have the same function on both sides. At the first derivative, to show that it's continuous, we take the derivative of both sides with respect to x, really, and then plug in Cassie. We once again find that it's the same on both sides. Technically, the one on the right should be more complicated, but for the sake of typing and visualization, I kept it in the simplest form. And similarly for the second derivative. So not only do the slopes match, but the concavity matches at x equals Cassie at the knot. And that's problem number 1. Problem number 2, thinking along the ideas of what we encountered in previous chapters with ridge regression and lasso regression. Suppose that there is a new curve g hat that is computed to smoothly fit a set of endpoints using the following formula. So we recognize the method of least squares. We recognize a penalization term where g m is the mth derivative. And just in case, g0 is the constant, or the original, I should say. Like usual, we seek to minimize the terms. So what this is saying is we somehow have a space of many possible functions out there. We are seeking the best one that will minimize the errors amongst the, let's say, training set. So what the textbook problem asked was, in these pairs of scenarios, what type of function would we probably get for g hat? In part A, lambda is infinity, m is 0. What we're looking at there is a heavy penalization for all functions except for constants. So our g hat would probably be a horizontal line. In scenario B, lambda is infinity, m is 1. We have a heavy penalization of all functions except for linear functions. That is ones of the form a plus bx. Continuing right along, scenario C, lambda is infinity, m is 2. Heavy penalization except for degree 2 polynomials. Scenario D, lambda is infinity, m is 3. Heavy penalization except for degree 3 polynomials. That is, the degree 3 polynomial would be what's created in the modeling process. And then to throw in a little extra review here, the textbook authors asked about lambda is 0, m is 2. Well, if there's no penalization, then that might lead to perfect fit of the training data. Now it's all on this big formation up here.
Yeah, in that case, will overfit.
Yes, indeed. If, as we've seen in elsewhere, if we have a lot of fitting on the training data, most likely will overfit when we get to the testing data. For problem number 3, it's kind of annoying to read it all at once. All these I functions are indicator functions. That equals 1 over that given interval or 0 otherwise. If we had these indicator functions for B1, B and B2, we then ran a regression model on it as such and got these coefficients. Beta naught is 1, beta 1 is 1, beta 2 is -2. What kind of polynomial will we get? When you really double check everything, track everything through, at the top, we're really looking at a knot at x equals 1. And what would happen, long story short, is we would have a straight line from -2 to 1. And from x equals 1 to x equals 2, we would have a downwards facing parabola. They do meet at x equals 1, so continuity. And we could double check the derivatives to see if they're smooth as well. In other words, we have this piecewise function. Problem number 4, a more complicated version of problem number 3, indicator functions, makes a piecewise function in the background. We got or performed linear regression, got these coefficients for beta naught, beta 1, beta 2. Admittedly, I did not graph this one. The online graphing programs only looked for 2 pieces at a time. I could have made R code, but the overall point is that we can recover the piecewise function if need be. And then finally, the last of the conceptual exercises, problem number 5. You might want to debate this a little bit. There are 2 g-hat functions, kind of similar to what we saw above, where they are composed of method of least squares along with a penalization term. G1 is aiming at a 3rd degree polynomial, and G2 is aiming at a 4th degree polynomial. In part A, as we impose more penalization, which one would have the smaller training residual sum of squares, RSS? Looking at the training set, G2, being a 4th degree polynomial rather than a degree 3, has more flexibility, and therefore would likely have a lower training set RSS. Part B, similar question, but asking about the test set. Here, G1 will generally perform better than less flexible functions, but G2 will perform better on more flexible functions. In other words, when we're considering the polynomials, we probably want a lower complexity for lower complex data sets, higher complexity for higher complex data sets, maybe. And then one more time, if we have zero penalization, what would happen? If there's no penalization, the training and testing terms for the residual sum of squares errors will be equal. So those were the 5 conceptual questions of the chapters. Do you all have any questions or further thoughts on that?
No, it's okay.
No questions so far.
We'll move into the applied exercises, trying out some of these neat ideas about splines and GAMs. Using the wage data, this was presented a lot in the chapter in the materials that we explored last week. Remember, we're looking at how much money people make, and for the most part, we agreed that people, say, between the ages of 30 and 60 tend to make more money. What problem 6 is recommending at first is polynomial regression, but putting some of our ideas together, we could perform cross-validation on the generalized linear models. For each degree of linear polynomial between 1 and 10, we could build a GLM fit. Get to cross-validation errors, let's say doing that 10 times each. So 10 polynomials, 10 times each, 100 models. And we could look at the cross-validation error. We seek to, of course, lower the error, but not create a situation where we might create more variance later on. So here, the cross-validation error seems to be pretty stagnant after the degree 4 polynomial. At least this quick plot of the errors implies that we should be using a degree 4 polynomial. If we do look at the linear model for degree 4 polynomial and look at the summary statistics, we do so far have significance for the intercept, the first coefficient, second, third, and a little bit of significance even for the 4th coefficient. Another way to look at this is through ANOVA. We could start with a linear regression, degree 1 polynomial. We could also build the degree 2, degree 3. Let's go up to 5. Run this through an ANOVA procedure, analysis of variance. The summary statistics would indicate that going from degree 1 to degree 2 has a lot of significance, maybe brings in more information to our modeling. Going from degree 3 to degree 4, significance. Oh, sorry, 1 to 2, 2 to 3. Going from degree 3 to degree 4, maybe some lingering significance here. But going from degree 4 to degree 5, we do not see any more significance in this point of view. So the ANOVA check, as prescribed, stops showing significance after degree 4. And then looking at the graph with our degree 4 polynomial, we have a smooth function. We have some arguably tight or close confidence interval bands as well on our wage data. This was some of the behavior that we looked at last week. In the data, the younger people and the older people, for various reasons, tend to make less money. And a lot of outliers for the middle-aged people. In part B, let's try to consider some step functions. Perhaps in the data, there are certain reasons why there might be some change in the scenario as far as money making or wage earning. The person in the GitHub repo ran cross-validation error with various numbers of cuts. So say if we break this up into piecewise functions, how many cuts should we make? We could use cross-validation to try to help us find that out. We look at the graph, we could see that at about index 7, we have the lowest cross-validation error. Now, I probably should have gone back and reread the chapter a bit. The advice is to use 8, where it's index +1. At first, I was thinking that if you have 7 cuts, you would have 8 pieces for the piecewise function, but I'm not quite sure the intuition here otherwise. Proceeding with a generalized linear model with 8 cuts, we have this picture here. Once again, we observe that our model is pointing out that people in the middle ages of the age range tend to make more money, whereas the younger and the older people tend to make less money. Along with apparently pretty reliable confidence interval bands.
Why do you think that most of the layers are concentrated in the range? It seems like 30 to 60.
Yes, we are probably getting more cuts where we have many more data points, where we have what mathematicians might call adaptability. If, say, on the far right, if we don't have a lot of data points, we don't have to have the computer spend more time there. But on the left, where we have many data points, we have the computer spend a lot more time asking itself whether or not it's a good idea to make a cut, to make a new piecewise function. So it usually comes down to the sheer amount of data, but also, of course, if in the data itself, there's a lot of jumps in the behavior, if there's a lot of much larger values as well. In problem number 7, we're going to move on to looking at the wage data, but looking at categorical variables such as marital status. I prefer to use ggplot, so I went ahead and ran this graph in ggplot. Here's a quick box plot on the left, or actually the 5 categories for marital status: never married, married, widowed, divorced, and separated. We could see that the highest median wage is among married people, but also keep in mind that we do have some high wage earners forming outliers in some of these groups. If we run a generalized additive model, a GAM, on this model formula, remember marital status is a categorical variable. For the possible slopes for these categorical variables, we have these confidence interval bands. For never married, we have a fairly large confidence interval band. For married, we actually have a pretty assured small confidence interval band or error bars. But for the widowed category, we are seeing some very large error bars, which might not fit our intuition from the data itself. I did not include it here, but for the folks, the person that was making the GitHub repository, the solution, what they then did was look at the sample size for each of these 5 subcategories. It turned out while there were maybe around 200 never married people, 200 married people, etc. In the widowed category, there was only about 40 people there, a much smaller sample size. And that could be a consideration when making the generalized additive model. It's just that the follow-up calculation did not seem to change. So I wasn't quite sure what was going on there. That is, you could subset the wage to skip over the widowed people in category 3, but for some reason the GAM didn't change. At least when I was running the code. For another categorical variable, there was one called job class, which apparently split up all the jobs into 2 labels, industrial or information. And for when this data set was taken or assembled, which I believe was 30 years ago, maybe 20. The box plots imply that the median wage for information-based or information sector jobs was higher than industrial sector jobs. And looking at the generalized additive model, we do have some small error bars. And once again, a reflection that the industrial jobs made less than the information sector jobs. These plots for the GAMs, for the generalized additive models, were kind of strange to me. Do you folks have any more ideas of how to read these graphs or how to interpret them?
Not yet, really.
Neither.
In general, we do know that with more complicated models, the interpretability, literally how to describe them, is tougher and tougher. All right, so in problem 8, we'll move on to the auto data set, talks a lot about cars. And we'll use the miles per gallon, the gas efficiency, as our response variable. What we want to explore are situations that may be non-linear in behavior. So if you look at the middle of this pairs plot, we see a bunch of linear behavior between, say, displacement of horsepower and weight. But if you look at the very top, especially with miles per gallon as the response variable, we do see some situations that are obviously non-linear, such as miles per gallon with displacement, miles per gallon with horsepower, and miles per gallon versus weight. We'll look at horsepower first, and like we may have done in previous exercises, try out a linear regression model, a degree 2, degree 3, all the way up to a degree 6 polynomial. Running these ideas through analysis of variance, ANOVA, going from degree 1 to degree 2, that is going from a straight line to a parabola, would probably immediately make sense for these graphs that we see at the top of the pairs plot. However, going from degree 2 to degree 3, from degree 3 to degree 4, doesn't seem to add any significance. But the reason why the solutions kept going was going from degree 4 to degree 5 and going from degree 5 to degree 6 seemed to bring back some significance, implying that we might be able to get some more from our modeling process. Putting all those polynomials together on the miles per gallon versus horsepower plot, the linear regression in the blue dashed line, the quadratic regression, the degree 2 in the red curve, and the degree 5 polynomial in the bright green dashed line. So in other words, the blue line is probably not doing enough of a job summarizing the behavior. The red curve for the degree 2 polynomial seems pretty good in my opinion. But if we carried out more calculations, the degree 5 is probably the best in this scenario. All right, we're going to move on to problem 9, which I think was the longest one. The Boston data, if I remember correctly, 1970s housing data, trying to get a sense of what causes some locations to have low rent prices, what causes some locations to have high rent prices. Our predictor variable, I think I have these switched. Our response variable was the pollution level represented by nitrogen oxide concentrations. Our predictor variable was distance to employment centers. Something strange that came up when I was knitting this part of the book and getting the GitHub push to go through. The Boston data set is pretty ubiquitous. It is featured in some various packages that our programmers tend to use when we're studying. So if you happen to be using the MASS package, MASS, to help you with some of these regression ideas, but we're also studying from the ISLR book, this Boston data set was loaded twice. So in order to get the book, these book of slides to build, I had to specifically tell us which one we're using, even though they might have been the exact same data. All right, so we're gonna look at a generalized linear model, response predictor, maybe a degree 3 polynomial. And we have this behavior so far. Degree 3 polynomial arguably doing a good job summarizing the relationship between pollution on the vertical axis and the distance to employment centers on the horizontal axis. That is, if you live close to your job, chances are you lived in a part of Boston that had a lot of pollution. If you live far away from your job, chances are you lived in a suburb of Boston that had less pollution. We tried out a degree 3 polynomial, and for each degree, it seems significant so far. We could, of course, try out other polynomials. At this point, I took the recommendation of splitting the data into training and testing sets. There was some other code here, but to be honest, I forgot which package this code from. So I used base R instead to do the split. Have 80% of the data going into the training set, 20% of the data going into the testing set. Looking at polynomials, degrees 1 through 10, we could get this crazy situation here. Keep in mind, especially because of the way polynomials get towards the right side that's admittedly covered up by the legend. Predictions for the edges of the data set or extrapolation are pretty bad when it comes to polynomials. Plotting the residual sum of squares. This is maybe a subjective choice here, but we could probably be assured that having something around a degree 3 or degree 4 polynomial would be the best route based on what we're seeing. That is,
Could you go back to the previous picture?
sure.
I wanted to see if the polynomials of degree 3 and 4, do they explode for bigger x, or are they also falling towards 0 for greater x? Well, as we would expect.
So at distances between 10 and 12 miles, as you indicated, the greenish colors for those polynomials seem to still do a good job with their predictions.
Okay.
And as you all were talking about the bias variance trade-off in previous chapters, if we use a larger degree polynomial, we are indeed seeing a lot more variance in the testing stage. We could also use cross-validation to find a polynomial degree, like we did in a previous example. Ran the code for degrees 1 through 10. And once again, we find that with the cross-validation error, we're pointed out maybe a degree 3 or a degree 4 polynomial. We could then look at regression splines. In context, perhaps there are different neighborhoods. I'm biased because I come from an American city, and different neighborhoods might have different taxations, different housing prices based on based on where people live. So it might be useful to have models that are piecewise functions that might model the behavior of the different neighborhoods as far as distance from where people work, namely the commute or driving distance. So we could use splines, maybe going up to 4 degrees of freedom. At this point, I might know mathematically what degrees of freedom are, but I forgot what degrees of freedom means in terms of exactly in terms of the splines. Seeking out 4 degrees of freedom. So far, we have significance at all levels. And there was a neat feature that if you go in through this code and you look at the attributes, it will actually tell you where they broke up the function into multiple pieces, where the knots were. In this particular model, there was only one knot, and that was at the 50th percentile. So that is at the median distance for commute time. They actually broke up the model into 2 different pieces. So with that, it's not quickly apparent on this picture, but at the median distance, there's actually 2 pieces in here for the red line for the red model. And then once again, the confidence interval bands in the blue dashed lines seem to be pointing at some reliable modeling here. Being mindful of time, this overall example, problem 9, is probably the most interesting, and then we'll just briefly mention problems 10 and 11. Now, in the earlier example, we just happened to try out 4 degrees of freedom. Like what we did before with the polynomial degree, we could try many different degrees of freedom, maybe going from 3 to 20, and seeing what we have. Picture-wise, we have this. These are regression splines, meaning for each curve, they could be broken up into multiple pieces. And as compared to the crazier graph that we got before, we could see that the polynomials are more restrained, so to speak, and seem to fit the data better.
Yeah, each line is predicting really close to each other. It's not a big difference between the degrees of freedom.
Yes, indeed. And then once you, the machine learning analyst, gets used to the code, good idea to run it through cross-validation. If I was doing this professionally, I'd spend a lot of time here. The calculations are done through some matrices, so it's a bit more complex. But for the scenario above, we found that 8 degrees of freedom as far as how to make the splines and the piecewise functions seems to lead to the lowest cross-validation error. This should probably say degrees of freedom. So now is problem 9 on the Boston data set. Again, this is probably the most interesting one today. Do you have any more thoughts or questions about it?
One question, when we find that a certain kind of optimal value for the degrees of freedom is 8, in the spline case, does that mean that the local polynomials that are going to be created they have degree 8 or what type of degree?
I'm not sure about that. Angel, did you have an answer to that one?
You repeat the question, please, Lucio?
Yes, so for that optimal value for the numbers of freedom that we found it to be 8 via cross validation, because we are working with the spline case, that number 8 degrees of freedom, does that mean that every polynomial that is going to be constructed in this spline fashion, is such polynomial going to have a degree 8?
I think you mean each polynomial, you mean for another predictors? For this one.
Yeah, in this example, in these polynomials of the spline case, if they have also degree 8
Mhm.
or less, because I would assume that they would have less, and these degrees of freedom is because we're defining piecewise functions. So that in itself, I mean, it's a kind of freedom. So I don't think that the polynomials have degree 8, but I am not sure. I am not sure. Then what would be the degree of those polynomials? Only 3, because that's usually the case for spline, or what?
Yes.
Okay.
So as Lucio is implying, when we're thinking about the splines, especially if we want the splines to, first of all, be continuous, but also be smooth or have the same slopes at each side, that's what the degrees of freedom are pointing out, the number of coefficients. So if you're asking for these to be clamped splines somewhere in the code, yes, we could take this degrees of freedom number and probably divide it by 2, give or take a little bit. And this would probably be implying a degree 3 or degree 4 polynomial.
And the division by 2, why was that the case?
Because if you're looking for both continuity and differentiability, it doubles the amount of equations that went into this.
Oh, yeah. Okay. Yeah, I remember when we saw in a numerical calculus course, then we did get that doubling of variables that you have mentioned.
Right.
Okay. Now it makes sense now. Thank you.
And let me just quickly mention the last couple examples. For the college data set, our response variable is out of state tuition. Predictor variables of all the other variables that could go into this. Once again, I split up the data using base R to get the training and testing set. We could look at forward stepwise selection of the variables using the function that was prescribed earlier in the chapter, or actually in the previous chapter. And for the various models that were found for how many variables we could use, there are different metrics that we can use. We could look at the lowest Bayesian information criterion. It's probably a little easier to see on the graphs. We could look at the CP metric, the BIC, or the adjusted R squared coefficient of determination. And we find that, especially for BIC, we have the lowest around 10 variables. Can anybody remind me what CP meant in this context?
It's an approximation to a standard error. To the test is standard error because it's using the trained data to calculate and estimate that.
Okay, thank you.
And the big is just the same metric, but a higher penalty for adding more predictors.
Oh, right. Thank you. Likewise, adjusted R squared is literally adjusted for penalizing for number of predictors.
Correct.
So say if we looked at the forward selection model with some of the variables, we could get coefficients thereof to predict the outer state tuition. If we looked at this in another modeling procedure, generalized additive models, we could build our GAM using splines for each of those variables. For the categorical variable on the top left, we could see the result there. The rest were numerical variables, and you could see, depending on the situation, we have, loosely speaking, a different degree of polynomial. We have perhaps these models broken up into piecewise functions into multiple pieces. Quickly looking at some models, if you look at a model without the graduation rate, with the graduation rate, and then with the graduation rate, but with a fourth degree spline there. The modeler found that we have significance adding on to graduation rate, maybe adding a little bit more there, but getting the spline on the graduation rate might not be that useful. So just a lot to think about. I guess what the point of this question was, if you were then asked to add a predictor variable to your model, how you should do it, or how you should double check yourself doing it. And then finally, problem number 11, exploring backfitting. The idea here was, if you have multiple linear regression, what problem number 11 prescribes is another way to do that in case you might run into heavy load times, or your calculation times are taking a long time. So say if we had a polynomial, or sorry, if we have linear regression with x1 and x2. The strange thing is, you could just pick some number for beta 1 and figure out what beta 2 is. Then go back and say, well, it's beta 2. You could figure out what beta 1 is. That is, you fix one number and figure out the other one, and you do that one at a time. I'll just read the rest off pretty quickly. If you run this through a big for loop, you could do that hundreds of times. But even after just 5 iterations, here are the coefficients for the linear regression. We compared that to the linear regression that we get from base R, and we find that this strange procedure, after just 5 iterations, seems to converge pretty well to what we wanted. Problem 12, similarly for backfitting. There's some matrix math in here, which admittedly I'm not going to read off right now. Here are some of the coefficients if we used base R. And it's pretty neat. This is done on matrices. Whereas with the improvised algorithm, where you kind of go back and forth, setting one to be constant, finding out the other coefficients, we find that we get, after about 25 iterations of the procedure, we get convergence on pretty quickly on what we wanted in the first place. So it's a curious computer programming exercise where you could perform multiple linear regression, but in a different way, just in case. And again, I think it's just in case you run into complicated calculations that take a long time. And that brings us to the end of chapter 7.
Great, thanks.
Okay, thank you very much, Derek, for the presentation. Well, I have already signed up for the next chapter, so next week we will be taking a look at three waste methods. I think they are quite drastic from what we have been covering in the last weeks because they are mostly regressions using lines or polynomials. So it's going to be interesting. Seems to be pretty different. So I hope to see you next week. Bye for now.
Thanks, guys. Bye.
Bye bye.